oscillations. Oscillations. What does oscillate mean? To oscillate means to go back and forth. Is that right? Yes. I have an example of an oscillation here. Now, this is a loaded spring. If you look at the spring, a mass is suspended from there. The position of the spring, the mass now, this position is called its equilibrium position. Now, if I pull it down from the equilibrium position, if I pull it down, what happens? I would want you to watch what happens. I'm stretching the spring. When I stretch a spring, you know, I supply that with potential energy. So, the spring is stretched, it has potential energy. So what happens when I leave this mass? Because of the potential energy, the spring will do work. There you are. Setting the mass into oscillation. Now, if you look through the energy changes, we will be looking at this as we go on. The stretched spring has potential energy, and that potential energy gets converted to kinetic energy of the mass. The kinetic energy will compress the spring. You see how the spring gets compressed? The compressed spring has potential energy, and that potential energy will then push the mass back, giving its kinetic energy. You can see energy gets converted from potential to kinetic and back at a continuous rate. And this is an example of oscillation. Alright, let's talk more about oscillations. If a loaded spring is pulled down and released, the system moves up and down. I have an illustration here. The same thing I just showed you. The system moves up and down about its equilibrium position. You understand what that equilibrium position is? Well, the equilibrium position is over here. It goes to a lower extreme, comes back to the equilibrium position, then goes to an upper extreme, and the oscillation is between a lower extreme and an upper extreme. This up and down motion of the load is called an oscillation. So an oscillation this is a good example of an oscillation, the up and down motion of the load attached to a spring. When the load is pulled down to the lower extreme, this is the lower extreme, the work done in stretching the spring becomes potential energy of the spring, which then pulls the load back, giving its kinetic energy. That means the load will now rush back to the equilibrium position. Alright? And now, when it gets back to the equilibrium position, can the load stop there? No, it cannot. Why not? Because it has now acquired a speed. You see, by rushing back because of the potential energy of the spring, it has acquired a certain velocity at the equilibrium position. Therefore, it cannot stop there. It will move up, compressing the spring. The kinetic energy at the equilibrium position does work in compressing the spring so that the load moves to the upper extreme. That is the upper extreme. Now, the compressed spring now has potential energy, and it does work pushing the load back to its equilibrium position. Now, that means the load now rushes back to the equilibrium position from here. But when it comes back to the equilibrium position, can it stop there? No. Why not? Because it has now a speed, and its speed takes it to the lower extreme, and when it does so, it will stretch the spring, giving the spring potential energy. Now you can see how the exchanges of energy take place. The spring has potential energy when the load is at either extreme. So the spring has maximum potential energy when the load is at the lower extreme and when the load is at the upper extreme. Now, in between, it has both potential energy and kinetic energy. Alright, at the equilibrium position, the potential energy of the spring is 0. Do you understand that? Well, at the equilibrium position, if you notice here, the load is now at the equilibrium position. Now the spring is at its natural length. The potential energy is 0. The potential energy is maximum when the load is at the lower extreme, and also when it is at the upper extreme, when the spring is compressed to its maximum. So the load has maximum, the spring has maximum potential energy when the load is at either extreme. And how about the energy of this mass? When will this mass have the maximum velocity? Its velocity is 0 at the lower extreme. Its velocity will be 0 at the upper extreme. Now, from the upper extreme it gets pushed down. So when will the velocity become maximum? At the equilibrium position. So the load has maximum kinetic energy because its speed, it has kinetic energy at the equilibrium position. So I hope you are able to trace the energy changes that take place during the oscillation. So let's look at the equilibrium position. At the equilibrium position, the potential energy of the spring is 0. The kinetic energy of the mass is a maximum. I hope you can read this. Potential energy is represented by U. I hope you know that. We discussed all that in Physics 1. K stands for kinetic energy. At the equilibrium position, the kinetic energy is maximum and the potential energy is 0. At the upper extreme, the kinetic energy is 0. The load is momentarily at rest at the upper extreme and the potential energy is maximum. The spring is compressed to the maximum level there. Similarly, at the lower extreme, the potential energy is maximum because the spring is stretched to the maximum and the load is momentarily at rest there. Its kinetic energy is 0. The amount of stretch of the spring from its equilibrium position is called the displacement Y of the load. You can see the load is at the equilibrium position. As it keeps moving up, the displacement Y, you can see at any particular position, the distance the load moves from the equilibrium position is called the displacement, and we will represent that by the letter Y. Now, can you look at this and tell me what is the maximum displacement of the load? The maximum displacement occurs when it is at the upper extreme. That means the displacement at that time will be this displacement where I have used the white braces. Now, this displacement is called the amplitude, represented by A. So what does the amplitude mean? Amplitude of oscillation is the maximum displacement of the oscillating object, and displacement is measured from where? From the equilibrium position. That means the displacement can be positive or negative. An upward displacement is positive and a downward displacement is negative. Alright? As the load oscillates between the two extremes, from lower extreme to upper extreme and back, the displacement y changes. Can you trace out and tell me how the displacement changes? Well, watch this carefully. At the equilibrium position, the displacement is 0. As the load moves up, the displacement increases, reaches the maximum. And what is the displacement when the load is at the upper extreme? It is the amplitude, the maximum displacement. And then the displacement begins to decrease, reaches 0, and now it is going to go down. The displacement now is negative. It goes to a negative minimum and then increases to 0 and then increases to a maximum, and that is how the displacement y changes with time. It's very important to know how that displacement y changes with time. Okay, so the displacement changes from maximum value a to minimum value negative a, and it increases to a maximum, decreases to 0, and decreases to a minimum, increases to 0, and so on. We will now obtain an equation for the displacement y as a function of time. Well, and that is the most important part of this discussion. We now need to represent the equation, or an equation for the displacement, in other words, as the load oscillates between an upper and lower extreme. You can see here, this is the equilibrium position. The displacement increases to a maximum, decreases to 0, decreases to a minimum, increases to 0, and so on. We will now obtain a mathematical equation for the displacement as a function of time. Alright, let's do that. Now, before I do that, I would like to show you a couple of examples of oscillations. Now, look at the same example here. The loaded spring is oscillating up and down, and look at how y changes. Y is 0 here. This is the equilibrium position. Y increases to a maximum, decreases to 0, decreases to a negative minimum, back to 0, and so on. And we are going to obtain a mathematical equation for the change in this y as a function of time. Now look at another type of oscillation. Now this type of oscillation is called a torsional oscillation. A torsional oscillation. And the displacement here is angular displacement. If you remember, we talked about rotational motion in physics 1. So torsion is actually rotation, and the displacement is angle theta. And angle theta is 0 at the equilibrium position. Theta increases to a maximum and then decreases to 0, decreases to a minimum, and then increases the same way as y changes. So y for this kind of oscillation and theta for torsional oscillation follow the same kind of change. Alright, let's go and look at another example. Let's look at this. Consider an object moving around a circle of radius a. Well, this is the circle. This object is moving around a circle of radius a. This is the radius a. Alright? At t equal to 0, what does that mean? We are now going to observe the object after starting a clock. Now t equal to 0 means at the instant I started the clock, where is the object? The object is here at P. At t equal to 0, the object is at P. A little while later, you can see the object is going to move around the circle. At t equal to 0, the object is at P. A little while later, it is at point Q. So that, I want you to watch here, as the object moved from position P to position Q, what happened to the radius? The radius rotated through an angle theta. And this is the angle theta. That means, as the object got moved from position P to position Q, the radius rotated through an angular displacement. We will represent that by theta. Alright, let's draw a diameter. This diameter is BC. BC is the diameter of the circle. And what I'm going to do is, I'm going to draw a perpendicular from Q so that it touches BC. This is a perpendicular drawn from Q. A perpendicular drawn from Q meets BC at O. Alright? Now take care, take note of all these small developments. Now, O is called the projection of Q onto O. O is called the projection of Q onto BC. The projection of Q onto BC. In other words, if I keep a light over here, the shadow of this Q will fall on BC. That will be the point O. So O is called the projection of Q onto BC. Alright? And now, I want you to follow the motion of this point O as the object continues in its path around the circle. Alright? Listen very carefully. If the center of the circle is the origin, so this is the origin here, the center of the circle. When the object is at P, where will be this projection O? When the object is at P, the projection will be at the origin here. Is that right? If I show the light now here, the shadow of this P will be over here. So, when the object is at P, its projection is at the origin. When the object is at Q, the projection has moved from the origin to that position O. It has moved up. And this distance it moves up is called the displacement. You see that? Why? The distance it moves up is the displacement of the projection. Alright, shall I say that again? When I start my clock, t equal to 0, the object is at P. When the object is at P, its projection is at the origin. And as P moves along the circle, what happens to its projection? It moves up on the diameter. And when the object is at Q, the projection is at O. That means the projection has now moved up through a distance y, and we call that the displacement. In other words, the movement of this point O is going to be exactly the same as the movement of the loaded spring. Alright? This is what I'm aiming at. Alright. Now, when the object is at B, the projection also will be at B. Is that right? You can see, as the object continues to move along the circle, the projection O will go up ultimately. When the object is at B, the projection O will also be at B. And what happens as the object continues to move down the circle? Well, y is now equal to a, the radius of the circle. You see, when the projection is there, this will be the value of y, which is the same as the radius of the circle. Now, what is the value of theta when the object is at B? Tell me. As the object moves from P to Q to B, the angle theta increases. And what is the value of angle theta when the particle is at B? It will be pi by 2, 90 degrees. Is that right? So when theta increases from 0 to pi by 2, what happens to the displacement y? Tell me. As theta increases from 0 to pi by 2, the displacement y increases from 0 to a. Here its value is a, the radius of the circle. Okay. What happens to y as theta increases further? You can see, as the object moves now down the circle, what happens to the angle theta? Watch my little pointer. I'm going to use this as a constant companion for my class. So, as angle theta increases from 0 to pi by 2, y increases from 0 to a, and as angle increases from pi by 2 to pi. Are you understanding this? The angle now increases from pi by 2 to pi. What happens? The projection has now returned to the origin. That means the displacement is now become 0. As theta increases to pi, y decreases to 0 because the projection will come back to the origin. Y will decrease to 0, and as theta increases from pi to 3 pi by 2. I hope you understand this angle we're talking about. This is pi by 2. Now increases to pi. What happens as the angle further increases from pi to 3 pi by 2? That means the object is now continuing on this part of the circle. Well, the projection O will now move down and approaches the value negative a. And then, as theta increases from 3 pi by 2 to 2 pi, the projection will go back to the origin. Y will increase to 0. In other words, y will increase from negative a to 0. Okay, the displacement y is a function of theta. In other words, the displacement of the projection depends on the angle theta. Is that right? One more time. As the angle theta increases from 0 to pi by 2, the displacement y increases from 0 to a. And as the angle increases from pi by 2 to pi, the displacement decreases from a to 0. And as the angle now increases from pi to 3 pi by 2, the displacement decreases from 0 to negative a. And as the angle increases from 3 pi by 2 to 2 pi, the displacement increases from negative a to 0. So the displacement is a function of the angle theta. The motion of O is similar to the oscillations of the loaded spring, isn't it? The projection that O is now, this is the equilibrium position of the O. It increases to the upper extreme, comes back to the equilibrium, moves to the lower extreme, comes back to the equilibrium, the motion of the projection is the same as the oscillations of the loaded spring. Well, let's say the center of the circle be M. Let's represent the center of the circle by M. Now, MQO, look at this, MQO is a right triangle. Is that right? Because this angle is 90 degrees. Why? Because QO is drawn perpendicular to BC. That means this triangle MQO is a right triangle. The length of the hypotenuse, can you tell me what is the length of the hypotenuse? MQ. That is the radius. And what is the radius that we call the radius equal to A? So the hypotenuse of this triangle equal to A, and one leg is the displacement. Is that right? This is one leg of that triangle, and that is the displacement. Displacement of what? Displacement of the projection O from the equilibrium position. Can you tell me, what is this angle? What is angle MQO? Any idea? Well, you know that line MP and QO are parallel, and this is a line cutting them. Therefore, this angle and this angle are corresponding angles. They are equal. The angle opposite to Y is theta. This angle is the same as this angle. That means this angle is theta. Now, we are now going to obtain a mathematical equation connecting Y, the displacement of oscillation, to theta. Can you give me a mathematical equation connecting Y, theta, and A? Remember, the distance, the hypotenuse, the length of the hypotenuse is A. In the right triangle MQO, sine theta, look at this, sine theta is opposite side divided by hypotenuse, which is Y divided by A. Sine theta equal to Y divided by A, and therefore solve for Y from there, multiply both sides by A, you get Y equal to A sine theta. That means Y is a sine function. If you notice here, I have actually traced out the path that will be taken by the projection. The displacement increases to a maximum. When does the maximum occurs? When the angle is pi by 2. Pi by 2 is 90 degrees. When the angle is 90 degrees, the displacement is maximum. And the displacement decreases to 0 when the angle is 180 degrees or pi radians. And the displacement decreases to negative A when the angle is 370 degrees, and the displacement increases to 0 when the angle is 2 pi or 360 degrees. Can you figure out this graph? What is the function? What function has this kind of a graph? Well, this is a sine graph. Look at this. Y equal to A sine theta. Y varies according to the sine of angle theta. Now, Y equal to A sine theta, we have now expressed to Y the displacement of oscillation as a function of the angle theta. But we want to express Y as a function of time. How will we do that? Well, do you remember the concept we discussed in Physics 1? the angular velocity when an object is revolving around a circle. What is the definition of angular velocity? You see, as this object goes round, the angle theta is increasing steadily. And what is the rate at which the angle increases? The rate at which angle is being described is called angular velocity. We represent that by the Greek letter omega. Is that right? I hope you remember. Omega is the rate at which the angle is being described. Omega equal to theta over t. What is the unit of omega, the angular velocity? Angle is measured in radian and the time is in second. Therefore, omega, the angular velocity, is measured in radian per second. Now, don't get carried away when I have marked the angles in degrees here, but when you represent these quantities, these mathematical equations, do not use degrees, angle in degrees. They use angle in radians. So, angle should be always represented in radians. Now, solving this equation for theta gives me theta equal to, can you solve it? Theta equal to omega times t. So theta equal to omega t. Well, what all we need to do is, in the equation for y, replace theta by this quantity. And what is the equation for the displacement y? We have y equal to a sine omega t. Now look at this. We have now obtained an equation for the displacement of the oscillation as a function of time. Y equal to a sine omega t, where omega is the angular velocity, or sometimes it's called the angular frequency. Omega is the angular frequency of oscillation. Well, when omega is a constant, y depends only on time. Now, in normal oscillations, omega will be a constant. In other words, the rate at which the angle is being described remains a constant. That means when omega is a constant, y, the displacement of oscillation, depends only on this time t. So we have y is now expressed as a function of time. Y equal to a sine omega t. Now, the vertical oscillations of a load attached to a spring is similar to the vertical oscillation of the projection. You see, the oscillations of the projection O is exactly the same as the oscillations of the loaded spring. Therefore, we can take that equation and use it for the loaded spring. The displacement of the oscillating object is given by, therefore, y equal to a sine omega t. Now, can you draw a graph of that, a sine graph? The displacement is given by a sine omega t, and the graph therefore will be at t equal to 0, the object is at the origin, and as t increases, the displacement increases to a maximum, it decreases to 0, it decreases to a negative minimum, increases to 0. That is one full cycle, and the graph of the displacement will be a sine graph. So this graph represents the variation of the displacement. You can see from 0 to pi by 2, the displacement increases and reaches the maximum. From pi by 2 to pi, the displacement decreases to 0. From pi to 3 pi by 2, displacement decreases to a negative minimum from 3 pi by 2 to 2 pi, the displacement is back to 0. So this represents the displacement of the oscillating object for one full cycle. Now, what is one full cycle here? If you look at the object here, one full cycle is, this is the equilibrium position, it goes up, maximum displacement, comes back to displacement 0, goes to the lower extreme, displacement is a minimum, comes back to the equilibrium position. This is one full oscillation, and during that one full oscillation, the change in the displacement is given by this sine function, y equal to a sine omega t. Here A is the amplitude of the oscillation, isn't it? A is the maximum displacement. Now, this is a measure of the amplitude. That is the maximum displacement. So, that is the amplitude of oscillation, which is the radius of the circle. Now here, we assume that when t equal to 0, the oscillating object is at the equilibrium position. Now, this equation is true only if the oscillating object is at the origin, at the equilibrium position, when you start your clock, and it begins to go up, then back, and so on. On the other hand, if the object is at any other position when you start the clock, then this equation needs to be modified. Alright, that means this equation corresponds to theta equal to 0 when t equal to 0. Is that right? When t equal to 0, theta equal to 0 means the object is at the equilibrium position. Now, on the other hand, at t equal to 0, if the object is at B, that is here, alright, that means at t equal to 0, we have already covered an angle pi by 2. When you start your clock, if you start your clock when the object reaches the upper extreme, that means the angle is no longer 0, the angle now is pi by 2. So, if at t equal to 0, the object is at B, this corresponds to an angular displacement theta equal to pi by 2. Therefore, the equation of the displacement needs to take that into account. Now, how will the equation change? The equation will now become y equal to a sine omega t plus pi by 2, because the angle has now become pi by 2 when you start the clock. So your equation now has to be modified, y equal to a sine omega t plus pi by 2. Now, can you use your trigonometry to expand that? If you expand that, you will see this is equal to a cos omega t. Do you know how to expand that? Well, let me see. How many of you know? I know many of you don't. How many of you know the expansion of sine a plus b? That will be sine a cos b plus cos a sine b. Have you heard of that equation in trigonometry? Sine of, well, let's get away with that a. We need only sine. I don't want that a there. But let's cut that a off. Sine of a plus b equal to sine a cos b plus cos a sine b. In this case, our a is omega t and our b is pi by 2. So, if I replace A by omega t and B by pi by 2. Let's see what that will bring us. That will be sine of omega t plus pi by 2 equal to sine of omega t cos of pi by 2 plus cos omega t sine pi by 2. Now what all I did is replace A by omega t and B by pi by 2 to get this. Alright, tell me what is the value of cos pi by 2? I want to know how many of you know that. Cos pi by 2, cos of 90 degrees is 0. So cos pi by 2 is 0, which means that term will disappear. This will go because cos pi by 2 is 0. And what is the value of sine pi by 2? Those are basic things in trigonometry. Sine pi by 2 is 1. So this quantity will reduce to cos omega t times 1. Look at this. Sine omega t plus pi by 2 is cos omega t. That's what this equation is. Okay. Well, at least some of you knew that. Is that right? So, if when you started the clock, the object is at B, then the equation becomes y equal to a cos omega t. It is a cosine graph. Look at the graph of the cosine function. The displacement is maximum at t equal to 0. Displacement is 0, reduces to a minimum and increases to a maximum. The angle pi by 2 is called the phase angle of the oscillation. What is the meaning of phase? P-H-A-S-E. Phase tells you where exactly is the object when you start your clock. You see, if theta equal to pi by 2, it tells you directly that when you start the clock, the object is at B. Well, let me ask you this. Suppose the object is at the origin and instead of moving up, it is now going to move down. What is the phase angle at that time? If the object is at the origin and it is beginning to move down, it means it has gone up and come back. That means the angle has now become pi. The phase angle at that time is pi. What happens when you start the clock? The object is at the lower extreme. What is the phase angle then? The phase angle will be 3 pi by 2. That's right. So here the angle pi by 2 in this case when the object is at B is pi by 2. The phase angle tells you exactly where the object is when you start your clock. Now we will represent the phase angle by the letter delta. If delta represents the phase angle, then the equation for the displacement, we can now replace this pi by 2 by this delta. So what is the general equation of displacement? The general equation is y equal to a sine omega t plus delta. This delta, the value of that delta will tell you where exactly the object is when you start the clock. If delta equal to 0, the object is at the origin and is beginning to move up. If delta is pi by 2, when you start the clock, the object is at the upper extreme and is beginning to come down. If this delta is pi, it means the object has actually gone up and come back to the origin and is now beginning to move down. If this delta is 3 pi by 2, it means the object has gone up, come back to the origin, and has now gone all the way down. It is at the lower extreme. And delta can have any intermediate value. When the oscillating object is here, delta has a value. So what does the value of delta really tell you about the state of oscillation? It tells you where exactly is the object when you start your clock. There you are. This is the oscillation, and when you start the clock, when the object is at the origin, the displacement will be a sine function. You can see it traces out that sine graph. So the displacement for vertical oscillations, you see, normally when you measure distances in a vertical direction, we call it y. What do you call if distances are measured in the horizontal direction? We call it x, don't we? So the displacement for vertical oscillation is y equal to a sine omega t plus delta. You see, an oscillation can also be horizontal. Have you seen a horizontal oscillation? Well, let me see if I can show you a horizontal oscillation. Now look at this oscillation. You can see a spring. When you pull on the spring, you go to the right extreme from the equilibrium position, and if you leave it, the mass will oscillate between a left extreme and a right extreme. Now displacement in this case will be measured as x equal to a sine omega t plus delta. So you can have a horizontal oscillation or vertical oscillation. Depending on the displacement is vertical or horizontal, we will use x or y to represent that. Okay. So what will be the equation for that oscillation? For a horizontal oscillation, x equal to a sine omega t plus delta. All right. Let's now write the equations for position, velocity, and acceleration of an oscillation. When we have an equation for the displacement, that is actually the position function, because the displacement tells you where exactly is the position of the oscillating object. So we already know the position function. The position function for such an oscillation is y of t, y as a function of time, is a sine omega t plus delta. That represents the displacement, but that is the same as the position function. Now, you know from your discussion on Physics 1, the derivative of the position function will be the velocity function. If this is the position function, can you find the derivative of this? And give me an expression for the velocity function. Now, you know that the derivative of a sine function is a cosine function, and this will be therefore the derivative of sine omega t plus delta will be cos omega t plus delta. Look at this quantity. Now, you must understand that derivative of, now listen to me carefully, derivative of a sine quantity is cosine of the same quantity, and you got to now multiply that with the derivative of this quantity. What is the derivative of omega t plus delta with respect to t? T is the variable there. Omega and delta are constants. So what is the derivative of omega t plus delta? it's omega. So the derivative of this function will be omega times cos omega t plus delta. I hope you understand that. Alright, this is the position function, which is a sine function. Y of t is a sine omega t plus delta. Velocity is the derivative of the position function. Alright, therefore v of t is y prime t, which is a omega cos omega t plus delta. One more time, the derivative of a sine quantity is a cosine same quantity multiplied by the derivative of that quantity. The derivative of omega t plus delta is omega. So a is there. A omega cos omega t plus delta gives you the equation for the velocity of oscillation. Tell me, where is the velocity maximum? The velocity is maximum at the equilibrium position, and velocity is zero at the two extremes. Is that right? Yes. Alright, so if I now draw the graph of the velocity, velocity is a cosine function. Look at the cosine graph. This is the velocity function, v of t equal to a omega cos omega t plus delta. What about the acceleration? Acceleration is the derivative of the velocity function. If this is the velocity function, what is the acceleration? Can you find the derivative of this? The derivative of a cosine quantity is negative of sine of the same quantity, and of course you need to then multiply with the derivative of this quantity. Derivative of this quantity is omega. So, and one more omega will get multiplied here. It will become negative because the derivative of cosine is negative sine. So what is the derivative of this quantity? It will be negative a omega squared sine omega t plus delta. So acceleration is negative a omega squared sine omega t plus delta. Now, can you tell me, where is the acceleration maximum? As the oscillation continues, where is the acceleration maximum? I want to bring this back over here. Now watch here. When I pull it down, you notice that the force is maximum on the mass now. Now, when the force is maximum, acceleration will also be maximum. The maximum acceleration occurs at the lower extreme and the upper extreme. When the object is at the upper extreme, the spring is completely compressed. That means the force is maximum now. So, when do the acceleration become maximum? Acceleration becomes maximum when the displacements are maximum, or at the two extremes. What is the acceleration at the equilibrium position? At the equilibrium position, there is no net force on the mass. There will be no acceleration. Now, you must be able to explain these in a sufficiently satisfactory way. So how does the acceleration of oscillation change? The acceleration will be zero at the equilibrium. The acceleration will be maximum at the upper extreme and maximum at the lower extreme. That means as the spring gets stretched, the force increases, the acceleration also increases. The acceleration reaches the maximum when the stretch is maximum. Also when the compression is maximum at the two extremes, where the forces are maximum. Alright, let's move on. So the acceleration is negative sine function. Look at that. This is a positive sine function. the displacement or the position function. Acceleration is a negative sign function. A of t is negative a omega squared sine omega t plus delta. I want you to concentrate on this equation for a while. Are you listening to me? Look at the position function. A sine omega t plus delta is the displacement equation. So if you come down here, watch this. A sine omega t plus delta. I'm going to remove this quantity and replace it by y, because y is a sine omega t plus delta. But because a sine omega t plus delta equal to y, we can now write the equation for acceleration as a equal to negative omega squared y. A very important equation. A equal to negative omega squared y. Don't you ever forget this equation. The acceleration of an oscillation. The acceleration of an oscillation is negative omega squared y, where omega is the angular frequency and y is the displacement. Now look at again. Acceleration becomes maximum when y is maximum. That means at the lower extreme and at the upper extreme. Okay. A equal to negative omega squared y. This suggests that acceleration of the oscillating object is directly proportional to the displacement. Is that right? Acceleration varies directly as the displacement because omega is a constant. So this equation suggests that acceleration of the oscillating object is directly proportional to the displacement and is directed opposite to it. That means, what is the direction of the acceleration? As y increases, acceleration increases, but as y increases upward, the acceleration is downward. As y increases downward, the acceleration is upward. The direction of acceleration is always opposite to the direction of displacement. That is what this negative sign says. So watch the sentence again. Acceleration of the oscillating object is directly proportional to the displacement and is directed opposite to the displacement. Now, such a periodic motion. What is a periodic motion? A periodic motion is a type of motion that repeats itself in regular intervals, such as the oscillations of a loaded spring. A periodic motion where the acceleration is proportional to displacement and is directed opposite to it is called a simple harmonic motion. So the oscillations of a loaded spring is a simple harmonic motion. And the acceleration of a simple harmonic motion is given by this equation. A equal to negative omega squared y. So you must be very familiar with simple harmonic motion. And all our discussions on oscillations will be on simple harmonic motion, or SHM. Alright, we will now talk about period, frequency, and so on of a simple harmonic motion. What are period and frequency of simple harmonic motion? Subtract